been doing this exascale stuff now for, shoot, 10 years. I led the exascale effort back in the 10 years ago for DARPA, the original technology study. And so at that point, I started gathering statistics to look at future projections of things and what have you. And what I've got here incorporates a lot of the non-traditional kinds of computations that I think we're going to see in the future. And the fact that it's on data-intensive day turns out to be great. The other part of my title is the third wall, and that's because I think all these data-intensive apps have in fact introduced us to a new wall in computing, and I think that's going to require innovations in architecture. So that's the three things I'm going to talk about. In terms of what I mean by why do we need new architectures, if you look back over the past, and I'll do this briefly with you, the long-lasting architectural changes that we've seen have always occurred when there's been some sort of a wall. And the first wall was the memory wall in the 90s, and most of you look too young to remember that. Then there was the power wall of 2004, and even there I'm probably skirting a lot of age. So I do think right now, and this is what I'm going to try to convince you, that there's enough evidence that we probably are looking at a third wall that I'll call the locality wall. And as I said, this is due to the fact that a lot of the applications we're looking at have a lot of data-intensive properties that don't work so well in conventional architectures. So by data-intensive, I mean that the computation is dominated by moving, accessing data, and it's not by flops. And in fact, in most cases, you look at the flops capability of the cores are essentially irrelevant to figuring out what the performance is. Also, lots of the data sets are persistent, but when you use them, you'll touch them once, the individual components once, and never little reuse. No predictable regularity in either how you access it or how you move it around, and scaling in particular. And I've got a really interesting chart that came out of reading the tea leaves on this stuff that show that there's some interesting scaling things that we haven't perhaps considered before, that in order to really increase performance we're going to have to handle. And then finally, streaming. A lot of apps, you think of the Internet of Things and what have you, there's a lot of streaming that goes on, and it's worth giving an example or two of how that affects architectures. So I'm going to talk about 4 topics. I'm going to go back and touch very briefly on Moore's Law and what went into the first prior walls. I'll talk then, kind of summarize what that means, where we've ended up in terms of architecture today, then talk about the evidence for the new wall, and then I'll also, because this is, I said, the need for new architectures, I'll throw out one new idea that's a possible fix. That happens to come from a startup of mine, but that's okay. So technology, Moore's Law. Moore's Law basically said that the two-dimensional transistors that we've known and loved get smaller and faster, and since the first microprocessor until today, that feature size has gone down by a factor of like 2,000, and that means the density has gone up by the square of that, like 4 million times. So that's what Moore's Law has been, and that's in fact what's driven things. And what that really meant is that for most of the lifetime of Moore's Law, cores got smaller, faster, and lower power, and the power density in particular, and this is what caused the second wall, was approximately constant as long as your voltage that you drove the chips at could continue to decrease. And as we'll see, it stopped. Memory arrays, on the other hand, got denser. They didn't get faster, and this is because of the topology that dense memory arrays have to have, and certain ratios of capacitance and what have you, which are kind of independent of some of the transistor speed. So we've been able to increase the bandwidth out of memory parts and increase the density, but we haven't really increased all that much the latency out of the parts. And after Moore's Law, what are we doing? And we're just about at the end of Moore's Law. We're seeing IBM announce that they've manufactured some 5 nanometer parts. So we're probably going to go 3D. And this is going to be a good part of where I think we're going to go in the future. This is a diagram of a Micron HMC part, which is a 3D stack of memory parts on top of the thing on the bottom. The blue thing is yet another chip, which is a logic chip. So there's a logic chip with a stack of memory parts on top of it. And I think that's where the real innovations of the future are going to come from. Just to talk of the memory wall, this figure over here is relative performance. This is up through maybe the 90s, early 2000s. CPU performance was growing at 60% a year. The performance curve for memory, which is essentially 1 over the latency, how fast can you access individual pieces of data, instead increased at about 7%. So you can see there was a huge gap. And what happened is after a while, the core clock speed so much outran the memory latency that you run a program on these things and you're dominated by memory time rather than core time. So how did we break the wall? You know, this is now over 20 years ago. We used the extra transistors from Moore's Law to build bigger on-chip caches. And more ILP to find more addresses to access these caches and additional floating point capability. And we were able to do this because the applications that people thought they cared about at the time had plenty of locality. And as an example, solving a matrix AX equals B, where A is a really big matrix and it's dense, and B is a dense vector. It turns out there's tremendous locality here. In fact, if you look at the typical calculations that go on LinPack, and this is the basis for how we rank the top 500 machines today, if you assume a cache can save a patch of the matrix A, and you read an n by n patch out of A, stick it in the cache, that takes your order n squared data movements. But if you look at the computations you do, that's order of n cubed computations. And what that really means is if you throw enough transistors at a big enough cache, I don't care how slow the memory is. I can just read in a big enough piece that I can keep the processor busy. This n squared to n cubed ratio, I can keep those cores doing useful things all the time. And we see that actually in the top 500. If you look at the efficiency of those machines, they're all 80, 90% of the flops are actually usable. So as I said, big enough cache, I don't care how slow the memory is, I can keep up. Power wall. So caches solved the first wall. Power wall came about. The curve up in the upper right is 3 different voltages: logic, low power memory, and high power memory, and over time. And you can see that they're decreasing very nicely, in nice exponential kind of rhythm until about 2004, where they begin to flatten out. And at this point, they're almost flat. There's no decrease in the voltage. And what that means is that the decrease in voltage can't offset the increase in clock rates that we wanted, and the increase in density, which increases the number of transistors on a square centimeter die. And that meant that power density started increasing. And the result, this middle chart here, are real parts, the power dissipation by those chips. And somewhere around 2004, we maxed out at about 120 watts, which is about the most you can cool without going into heroic efforts like you see today in some of the NVIDIA GPUs and what have you. So that 120 watts has been kind of the limit for conventional parts. Breaking the wall in this case required lowering the clock rate and then using multiple simpler cores. Rather than throwing everything but the kitchen sink and increasing ILP, you use a lot more simpler cores, which are more energy efficient, so they will do independent operations, and you increase the SIMD style parallelism. And the side effect for this is you do need more bandwidth, and the solution again for that is we spend even more transistors for caches. So today it's not unusual. You know, a conventional microprocessor might have 40 to 60 megabytes of cache in it. And this last curve down here is in fact clock rate over time, and the red line is again 2004. And at 2004 we peaked out at about 3 gigahertz, even though, you know, the parts we build today could probably run at 10 without any difficulty. So 2004, I said the architectural trick was the emergence of multi-core, and this is just a chart of the number of cores on a typical socket in a top 10 supercomputer over the years. And you can see we were just about at 1 until 2004, and then there's this is a logarithmic graph, so this is a huge, almost 2-order magnitude increase. And today, this is a recent Intel part with 28 cores on it, a 14 nanometer part, and this is a NVIDIA, the newest NVIDIA CPU. It has 84, depending on how you count cores, it's either 84 cores or just under 6,000 cores. So a lot of independent operations that go on. And what that means is that, you know, look at most supercomputers today. The architecture looks like on the right. You have a bunch of conventional sockets that have multiple memory channels that go off to DDR memories. And there are these orange links, which are coherency links that keep track of who's accessing what and how to make sure that somebody isn't writing over something that you think you have it in your cache. And then connected to these guys are these GPU chips that have their own multiple memory channels, and these are high-speed GDDR memories that you have to connect. And the whole thing, all these guys then have ports that go off to a network part. You were talking about I/O today, so network interfaces are part of that. And so in this thing, if you look at this and you pretend you're a thread buried in one of the cores down in here, or maybe even worse, one of the cores up in here, nothing is uniform about memory access now. There's multiple different memory domains on the same socket, on the different sockets, all over the system. There's multiple different types of memory ports and types, multiple different link protocols. Higher bandwidth parts are needed, which expend more energy. And in many cases, to get further, we've increased the width, how much data we bring back on an access. So that means we've increased the amount of prefetching, if you will, from each memory reference. And when you make a memory reference, if you only use 8 bytes out of 64, the other 56 bytes that you fetched are totally wasted. So that's today. And if you look at energy of these different things, this kind of brings it out in real contrast. First two numbers, these are for 28 nanometers, so this, again, is now a 5-year-old technology. The energy of an integer operation is about a picojoule. Energy of a floating point is about 20 picojoules. And then as you move up to do cache accesses or bus transfers on chip or off chip, or God forbid that you go off to memory or you know, a solid state disk or something, they increase tremendously to the point where, you know, you can modify these things. Today, these numbers are perhaps on the order of 5 picojoules rather than 20, but these numbers down here are largely unchanged because they're driven by different dynamics than Moore's law on chip. And which means that back when we did the exascale study, DARPA told us the goal for an exascale machine was 20 megawatts. And to get to that, you needed 20 picojoules per flop. And that's unreachable with any technology we could see then, and I think it's still largely the case if you ever want to reference memory. So if you're perfectly happy never referencing memory, I could probably build you an exascale machine. But be that as it may, we needed more bandwidth, so the newest thing people are adding are 3D stacks. I mentioned 3D is important, and these are called HBMs, high bandwidth memories, where you have a stack of memory, and they drive data down to the substrate, same substrate that the chip is on, not down to a printed circuit card, but to some sort of an MCM. So it's a low capacitance connection that you can run quite fast and quite densely. And when you do that, you get a tremendous bandwidth. You get 4 or 5 times the bandwidth that you get out of a DDR4 memory. So a lot more out of these. And this is, let's see, this is an NVIDIA, a recent NVIDIA GPU. There's that big monster chip surrounded by 4 of these little stacks to give it lots of bandwidth. And this is a Knights Landing machine from Intel, and there's 8 of these stacks next to it. So that's kind of where we are today, and that adds yet another memory layer to all those layers I just talked about in terms of things. So what I'm going to look at now are just apps, and this, as I said, I'm going to try to convince you that there's evidence that all this really means something different has happened. So I'm going to look back at our old friend LinPack. I'm going to look at HPCG, SPMV, sparse matrix vector product, breadth first search out of the Graph 500 benchmark, and then a streaming benchmark called Firehose. And we'll look at all those. And in these, I'm going to use a series of charts that all look the same. There's going to be 4 of these plots on each slide. And this is normally time, although there are some cases where it's not time. And this is some sort of a metric. So this chart is going to be performance and whatever metric is important to that benchmark against time. And this is peak flops of the top 10 machines. And you can see it's been growing nicely for 20 years. And the different colors and shapes, you can see the colors, but you can't see the shapes. There's actually 32 combinations here, which are different combinations of socket architecture and network architecture. So together, if you blew that up together, you'd see 32 different variations. And you could see somewhere around here, we switched from red to this mix of other colors, and that's where we started introducing GPUs into the mix and hybrid machines. So this is peak. The top 500 sustained. This is, again, solving AX equals B, where A is dense. That's also increased nicely. And this is all due to Moore's law. And what we did to fix that was keep growing the cache. HPCG, high performance conjugate gradient, does exactly the same thing. It solves an AX equals B, but in this case, it's A is a very sparse matrix. And each row has only 27 non-zeros in it, even though it may be millions of entries long. And in this case, you see that the performance in terms of flops has been flat basically since the beginning. The peak performance, there's been none of this exponential raise in performance. It's been flat. We haven't been able to get any better. And there's a reason for that I'll show you in a second. This is Graph 500. You've got a big graph and you start somewhere and you want to get to every point that you can touch in that graph. And again, there was for first year or two, there was a significant speed up, and this was due to people inventing new algorithms more than new hardware. But once everybody was using the same really good algorithm, there's been just a smidgen of performance increase, not much. And so this flatness indicates that it's something other than traditional Moore's law, which is limiting us. Something other than flops that are limiting us. So this is what I did here, because I'm interested in memory, is I've got performance per byte of bandwidth. So for each bandwidth in the machine, divide that into the metric, the performance metric, so you get flops per byte or TEPs per byte or whatever it is, again versus time. And in this case, you see that the peak flops, the LinPack numbers, again look good. We've been able to increase, again by increasing the cache size, increase the performance we get per byte of bandwidth. Bigger cache, as I said, allows you to do more. HPCG, this covers it up, but it's been essentially flat, as been Graph 500. So that means that the performance, now Graph 500 has been now over 6 or 7 years, we've gotten no better at getting TEPs, the traversed edges per second, out of machines. They're essentially been flat in terms of their use of bandwidth. And this is a little bit more enlightening. What I have here on the x-axis is not time, but performance. So the So to the right are bigger machines, faster machines with more capability. And again, the LINPACK numbers still look good. There's still you get to bigger machines, you're still doing things efficiently. HPCG is essentially flat. So it doesn't matter how big you build the machine, it's essentially flat. In fact, there was a really good paper that somebody wrote a couple years ago that analyzed HPCG and proved, to at least my satisfaction, that if you tell me the bandwidth to memory, I can tell you within about 3% the performance of the machine on HPCG without knowing anything at all about the cores. So it just is irrelevant. And Graph 500, there's actually a slight decrease over time as you get to these bigger systems, and that's because most of these guys have been built to do, the network topology has been built to do 3D scientific codes where you're always talking to one of your nearest neighbors in 3D, and Graph 500 has really random accesses to things all over the machine. And what that means is with a traditional topology, each node, particularly as you get to bigger nodes, more of the network bandwidth is spent rerouting packets that come in from neighbors and are supposed to go somewhere else. So that loss of bandwidth affects how much bandwidth that you yourself can inject into the system. So again, this is performance of byte per byte versus performance. The same kind of thing, LINPACK, very nice. HPCG is this flat, and again, Graph 500, this decrease is due to this network issue. This is another important. Exascale power has been the big problem over time. So performance per watt. LINPACK, things have been going as gangbusters as they have in terms of performance. This is performance per watt versus time, climbing all the time. Performance per watt for both HPCG and Graph 500 has essentially been flat. And in fact, if you look at, let me go ahead to this guy. If you look at just the Graph 500 in particular, and the x-axis in this case is edges, essentially the size of the graph. So bigger goes to the right, bigger graphs go to the right. Gigateps per watt is how much performance, how many units of performance do you get per watt in the machine. And the green squares, and I'll talk about the top three above the line in a second, but the green squares are all performance that you get out of one node, you know, a one blade, one node system. The blue squares are where you have multiple nodes. And what's really impressive about this curve is that again, this is a logarithmic curve, so from here down to here is 2 orders of magnitude. It's a factor of 100. So that curve is almost a perfect match to e to the minus 1/3, where e is the number, minus 1/3, where e is the number of edges. So the bigger the system, the worse the energy performance. The three guys on the top are all GPUs, and if you go back and look at those graphs all fit in their GPU memory. So you don't have to do any transfers out of that GPU memory. So this is kind of a neat summary that really looks at the scaling issues. And what I did here is I took those benchmarks that I was just talking about, and I found the best performance at one node, a one node system, and I normalized that to 1. So all of these things down at 1, the left side of the axis, they start at 1 just to normalize data so we can look at trends. And I've got this curve here is kind of a perfect scaling curve. If in fact you had perfect scaling, this is performance versus the one domain versus the number of domains, and that's where you would be. And asymptotically, all these curves begin to look like that when you get to big enough systems. So asymptotically, all these benchmarks, breadth first search, SPMV, HPCG, they all have really good weak scaling once you get to big enough systems. But in the region between 1 and, depending on the benchmark, 1 and 10 or 1 and 100 nodes, you lose somewhere between a factor of 10 and maybe a factor of 60 in performance. That then takes you a heck of a lot more nodes to put back into the system before you're back to what you were at one node. Okay, so this is, when I first saw this, I said, gee, this is really an interesting phenomenon that we're throwing away a factor of 60 to get something we can scale. So that's kind of scary. Other benchmark, last benchmark I want to just touch on is a streaming benchmark. And in this case, this came from Sandia. It's a benchmark for cybersecurity kinds of things. You've got a stream of packets coming in that have an IP address and a value. And the purpose of this thing is to look at all these packets and match up all the packets that have the same IP address. And when you've seen 24 of them from the same IP address, you declare that as an event. And then you look at the distribution of values that you can't come in. And if they look like they've been biased, you declare this is an anomaly and signal that to the outside world. So the performance metric in this case is datums per second. How fast can you shove data into the system and still process it? And there is some data on the web for this, and this is kind of a summary of it for a single, again, the single node issue is something important. So this is number of cores. The x-axis here is the number of cores you use in the analysis if you do it on a single node. And the dotted lines are the two lines are perfect scaling for two different forms. There's three different forms of this benchmark: anomaly 1, 2, and 3. The dotted line is for anomaly 1. The solid line and the solid dots are all anomaly 2, which is the more interesting one. And what's really important about this is anomaly 2, which is close to the real, has really terrible scaling. You go from one core to 7 or 8, 10 cores, and you picked up, maybe a factor of 60% in performance. That's not too swift. And the same phenomenon that you get good weak scaling. This is a system at Sandia, a Cray CS3000 with 2,000 nodes, and this gives data that goes up to about 300 nodes. And you look at that curve, and that's a pretty darn good weak scaling curve. Okay, in other words, the datums per second you get out, you add more nodes, you get more performance, and it looks pretty decent linear. So that looks good until you actually look at the numbers. One node, if you go down and look at the slope of the curve, the performance per node is about 2.7 million datums per second for a 32-core node. And the data I just showed you for single core, you could get about 2 million per second. So that says each core in this big system is giving you about 1/60th the performance that you'd get out of if you ran the problem on a single core. So this is another Houston, we have a problem kind of thing. Okay, so this is just the same set of benchmarks, and what I had over here are what the performance limiters are for those things. And in the four applications that are of real interest, the answer is they're all memory or network related. They're not at all related to flops or CPU architecture or anything like that. One other really interesting, and this is data intensive, and what I just had was benchmarks. So now I'm going to talk about a real application from LexisNexis. And just to set the stage, Geico, you have a website. Geico is a website. You can type in your information and get a quote back in, typically under a second. Geico has LexisNexis do all the processing from the public databases. And they, in 2012, when I did this study with Lexis, they had about 40 terabytes of raw data. They periodically cleaned it up. And what they did, and they still do this today, is they weekly boil the ocean. They take all the most recent public data, and this takes all weekend to do. And they pre-compute for everybody in their databases, which is now like 600 million people. Do they have financial problems? What's your legal problems, et cetera, all from. And then the really important ones, and this is why Lexis gets their money, is they also have been very good at computing relationships. Like, who has shared an address with X? Who has shared property ownership with X? And there's dozens and dozens of these relationships. And these are the real things that cause Lexis to make money, so that when Jane Doe types in her data and submits it, they look up all the answers for Jane Doe, and they can come back and say, well, Jane Doe doesn't have any problems, but she shared an address 3 times with Joe Scofflaw, and Joe Scofflaw has wrecked a couple of Porsches and had some DUIs, and you may want to take that into account. So that's kind of scary, but that's, that's what makes them money. And so anyway, if you did this traditionally, you'd end up with the problem is the intermediate, you're essentially doing the equivalent of a join in here. And the intermediate data set in 2012 would have grown to something like 300 terabytes. Today it'd probably be closer to a petabyte. And that's not something you really want to compute and then store somewhere and reaccess. So they have some really good ways using extraordinarily big hash tables, multi-level hash tables, to actually reduce the processing down to something that's almost linear. And so we built a model of this whole process, and we projected performance. In 2012, their base machine was 400 two-socket nodes. I looked at some future alternatives with them, upgrades to the conventional architecture, and that started with using things like ARMs in place of Xeons. Looked at that time, Sandia had a project called Excalibur, which looked at building a processor that was surrounded by memory cubes like the HMC, and today that really looks like Knight's Landing. Okay, so it's a very good analogy to Knight's Landing. And then I also looked if we threw away the Xeons. I hope there's nobody from Intel here. And just looked at putting processing at the bottom of the stack. And what we did is we built a model of the 9 separate steps and looked at 4 metrics that were part of that, one of which was CPU instructions per second, and the rest were bandwidth numbers, memory, network, and disk file system bandwidth. And so each of these 9 steps, the different colors represent one of those categories of metrics, and the tall poles in the tent are at each step what the bottleneck is. And as you can see, there's no one consistent tall pole. Sometimes it's red, sometimes it's blue, sometimes it's green. And what that means is that you just can't pop in a faster processor and expect something to work any better. In fact, we looked at varying everything. This was 2013. We projected ahead to, I think, 2020 or something, and estimated what the best you could have then were in terms of processors, memory bandwidth, using SSDs rather than flash, or rather than RAM disk, rather than rotating disk, I should say, and went to the fastest InfiniBand. And you use any one of those guys, and nothing gets you more than 45%. If you throw in all but upgrading the processor, you've got about a factor of, so you throw in 3 or 4 of them, you got a factor of about 4 in performance. If you threw in everything, you got a factor of about 8, and still in the 10 racks. And you say, gee, that's pretty good. But let's look at the unconventional numbers. So if you look at oh shoot, I should have done it in the other order. Let me do the lightweight one, the one in the upper right. So if you went to a system of ARMs, kind of like HP's Moonshot, or there was another machine, Calzada, that went out of business, a rack, 2 racks of ARMs gave you about the same performance as the 10 racks did, okay? The two-level memory, something like Knight's Landing, gave you, in 3 racks, gave you about the same time. But if you went to the 3D stacks and made some rational assumptions, you got like a speed up of like 200, and it only took 1 rack of hardware. So it just blows the problem out of the water. And that's because things are much more suited to the kind of application we had. So now I'm going to talk a little bit different. I'm going to make a suggestion on an architecture to kind of handle these problems. And this is a picture of an emu. So you might guess that my company's name is Emu Solutions. So, and an emu is a very fast, very curious bird. And the second largest bird in the world, in fact. So this all has to do with thread migration. When we talk about thread migration, we talk about moving it to a different site. And the reason we move a thread typically is to make memory references more local. And today that's either invisible. During an I.O. call, you'll suspend a thread and then wake it up on some other core when the I.O. call completes. And there are languages like Chapel where you can do explicitly. I don't know if you've talked about Chapel today or during. Okay. If you talk about Chapel, there are constructs in Chapel that allow you to specify where the thread should execute. So the new idea here is to make the migration automatic, so that whenever you go to reference something, you always make sure that reference is local. And so the notional migrational architecture makes what I'll call a nodelet as the unit of parallelism. It's a single memory channel, a chunk of memory, a memory front end, which is essentially memory controllers and some extra logic to do atomics, and then some number of somewhat specialized cores next to it. And so what you do is to build the system, you just have lots of these things. As I said, in this case, it should be the memory that's the unit of parallelism, not the core. And all the memories in this system all share the same global address space. And what's neat about this is a thread can start executing in one of these cores, and if it makes a reference to something that's not local, the hardware hits it over the head, puts it to sleep, ships it off to the right nodelet, wakes it up, and it starts executing, and the memory reference is guaranteed to be local. And it can also spawn new threads which can go off and do their own thing independently. So all the children can go wandering around kind of just like a herd of emus. That's the notional architecture. A real system that we've actually built has a nodelet that has 4 highly multi-threaded cores on it, so that we can have lots of threads. So there's always something to generate a memory address. That's why we multi-thread them, again, to keep the memory as busy as we can. And we can run a very rich suite of atomics right in this memory front end, so the time to do an atomic operation or synchronization or something else is almost as low as just doing a memory reference. So it makes it very efficient. And we put a bunch of those nodelets together on a single system. We have, this is a card that we built that has 8 nodelets on it, along with a dual power, 64-bit power chip on it to run a local instance of Linux and to launch the initial threads into the systems and to take exceptions and what have you. And combine a bunch of those with switches, and we have a system now that fits in a rack or in a desk-sized box that has 64 of these nodelets in it. And near term, we're going to take the same card and put a lot of these cards into a denser motherboard and stick a lot of these in a rack, so that we can get like 2,000 of these memory channels in a single rack. Just an example of how this might work. This is kind of a sketch of a simple sparse matrix vector computation. What you would do here is stripe the dense vectors across all the nodelets, and in each nodelet you'd also keep a linked list, the part of the linked list for each row that has non-zeros for elements that correspond to the dense vector. So that the traversal, a thread that's processing a row would simply traverse this linked list through this thing, and at each point, when it hits a non-zero, it'll go fetch the element out of the vector, do the multiply add, keep the sum, and then keep going, just following the list. So this is a pointer tracing machine that works pretty well. If you look at this and compare it to the data I showed earlier about SPMV, and I didn't mention, one thing I should have pointed out is the sparse matrix dense vector. If you're very, very sparse, which is probably the case when we look at a lot of the data intensive problems down the road, the performance on today's machines gets really terrible. This is these bottom lines, and here you lose almost 2 orders of magnitude in performance. If you look at this is measuring flops, since it's sparse matrix, it's a vector product. Flops is the unit of metric, so if I divide that by bytes of bandwidth to say how many flops do I actually get out of a byte of bandwidth, what it turns out, we're far more effective. This architecture is far more effective, these curves up here, at getting flops out of the system than the conventional architectures down there. And the streaming, the same way. The problem with streaming today is that cores don't really want to talk to anybody without big hardware stacks, you know, message passing or some of these other fish and water slide were the two others that people have used for streaming data from core to core. And we don't have to worry. And again, that's because there's this big hash table in the middle of this benchmark. And we don't have to do any exchange, talk to somebody else. The thread can just go there and do it. And the net effect is it looks like scaling on this thing just kills conventional architectures. We get that 60x back very easily. So the ultimate scaling on this, of where and I'm going to come back to the sea of stacks. This was our friendly HMC today. What I really want to get to is putting cores at the bottom of each fault and upgrading the off-stack interfaces to be essentially a network protocol. Add in a second stack of non-volatile memory if you don't get it with DRAM. And the result is one of these little stacks is equivalent to 32 nodelets. It's four of the boards that we have now. 32 memory channels and the associated cores just in a little memory stack. And then if you look at how we've talked about using these HMCs today, these silver things are, you know, today's heavyweight cores, and this is some sort of array of memory that's shared between these guys. What we're proposing to do is you can toss those guys out and allow the threads to be the glue that holds everything together. And if you go back and look at that LexisNexis problem I talked about, these are all the conventional upgrades I talked about. This x-axis is the number of racks. The y-axis is the speed up over the 2012 system. And this is all what you could do with architectures today. This is where I think we'd be with these migrating thread architectures. But particularly with this third one being a single rack of just memory stacks with the computing on that. So that's, you know, literally 2 orders of magnitude more at 1/10 the hardware, which sounds like that really is a neat problem. So anyway, conclusions. What I hope I've convinced you is that there's some really funny things that are happening in our memory system today that deal with locality. Current architectures are becoming badly inefficient at these things, and the problem is in memory and memory scaling and communicating between guys. And there's a growing need. I didn't really emphasize it here, but if you look at some of these problems, this idea of atomics turns out to be 10, 20, 30% of all the memory references that you really want to make. And today an atomic, you know, is you do an atomic and it's, oh gee, you know, you go to sleep for a while while you go out and do all the coherency actions and all this stuff to make it happen. Migrating threads simplify all this stuff, and there's a natural progression to 3D systems in general. So that's kind of my talk. This is just some acknowledgments, and I'm free to open for questions. And I guess there'll be a microphone. If you want to ask a question, grab a mic.
Any questions? Okay, I will break the ice. So how much time can take to develop a new memory? Because it looks like our machines are going faster or demand novelties that we cannot attain in the memory business. So I was curious about that.
Well, these new memories don't use any of the traditional Moore's Law faster well, they do use the denser transistors. But the real trick on those guys is when you stack them, you drill a lot. We've gotten very good at drilling lots of little vertical holes through a stack of these things and plating wires down through those holes. So the contacts, you can have, a normal memory part today has like 80 IOs that go off the chip. A lot of these stacks, you have several thousand vias, the TSVs that go down into the stack. And all of those are far lower capacitance than going off of a chip, which means you can run them a lot faster at a lot lower energy. So you get an absolutely incredible increase in bandwidth if all you're doing is going up and down the stack. And so the trick isn't in the design of the memory cells, it's in the design of how you put them together.
Thank you.
So all the different plots that you showed where there were performances for the EMU systems what of those are real measurements and what are projected?
Those are still projections. We literally just got working hardware maybe a month or so ago.
So all parts of the hardware or this desktop-sized machine?
The desktop machine, yeah, is working.
And what is your projected timeline or roadmap to get all the remaining things?
We should have a rack using we're using an FPGA right now for the core. So we should have a rack in well under a year. We'd like to put an ASIC in place of the FPGA, which would give us a big boost, and use an ASIC and some of those HBMs to give us even more bandwidth. That's a function of, you know, if somebody has an extra $20 million or so, that would be good. And then after that, and there's no real technological barrier for doing that. It's just money. And the 3D stack has got a little bit of engineering to do there. But that's also something, with enough money, you know, we could start that today.
Thank you. You said you are very good now to drill holes. So how do you do it, with optical lithography or e-beam lithography? Or none
no,
of this?
they just, gee, I don't even know how they just etch it. They're just etching. You know, the same way you etch out, you know, for vias to go between layers of metal.
So usually you first...
Yeah, now what
do
they do
lithography.
is they thin the back of the wafer. So the chip gets very, very thin. So the etching, the critical parameter there is the depth of the hole versus the width of the hole. And etching, you know, there's a ratio there. I don't remember what the ratio is, but there's a ratio there that if you go over, you know, you get the hole gets just too big and sloppy and what have you, or it doesn't form properly. So they thin back the chips, and that's an extra cost, so that you don't have to etch very far to get through.
Thank you.
There's one in the back.
I think I must have missed it when you were speaking, but so if I have a problem of like a halo exchange where I have memory that I have, but I need a row from a neighbor,
Right.
I can't go and do the process over, or the calculation on the neighbor, because I also have information that the neighbor would need.
Right.
And then, so how do you solve that?
With the migrating threads?
Yeah.
In that case, you don't necessarily need the halo unless you really want to, because you can just go there. I mean, they're all you have to make sure that your code node, and you have this problem anyway. If you're on one node and you want to multi-thread the computation, all those threads have to know how to deal with things that they might touch in common. And all we've done is say, okay, well, those threads need not be just from yourself. They can be passing by from any other, you know, started off from any other socket in the system.
Okay.
So are you also developing compilers for this?
Yes, yeah, we have a programming language. If you've ever heard of the language Silk, developed by Leislerson at MIT, that our tool chain uses an LLVM. It's an LLVM-based tool chain, and it executes Silk from that. And that's nice. What Silk has is it's C plus 3 primitives, a key one of which is a prefix you put in front of a function call, which says, when you do this function call, the caller doesn't have to wait around for the result. Okay, so you can split execution, and each one can go your merry way.
So going off his question a little bit, it seems more like these chips would do well in the job of say something like a GPU, or have you tried to compare with those sorts of work?
Well, GPUs, most of the GPUs really work best, again, at this business of relatively dense computation. I did show that for the best numbers for a single node for Graph 500 was the GPUs, where they all fit in memory. But the memory on a GPU is built to stream data and to do lots of semi-SIMD kinds of things across all those little small cores that go below one of the big ones. So once you get out of that range, in fact, an interesting thing to do that I started to do once, but I don't have, is a graph that shows the flops you get out, the growth in flops versus the growth in TEPs for the two. Because I think the number of TEPs you get out are, well, I know this is the case. If I go back, you know, today you can get a teraflop out of a GPU, and we don't get anywhere near a teratep out of any of those GPUs. Okay, there we go. This is, that's gigateps per watt. Okay, I have those numbers, and I guarantee you they're in a couple orders of magnitude different than the gigaflops numbers. So, you know, they work, but they have the same efficiency, kind of efficiency. You look at HPCG, which is also a sparse problem. Most of these machines on HPCG, you're lucky to get over 1%. And I think the really good machines get 4% efficiency of their flops. And that includes GPUs versus 80 or 90% if you're doing LinPack. So, anybody else?
When you migrate a thread from one location to another, still seems like you're doing a memory movement?
It's the state of it. Yeah, the state of a thread is about the same size as the state of a cache line. Okay. So if you think of if you were doing a remote memory reference on a normal architecture, you'd send a request out and you get that whole cache line back. And so if you send the thread out, the byte bandwidth that you need is about the same as the return, except that the latency is a half. Okay, because you don't have the return trip to make. So you're there. So the kind of problems that are really good are ones where you visit a part of a data structure and then you do a couple things to that and then you move on. If you're going to do something dense, go get yourself a Xeon or an NVIDIA. But if what you have is sparse, a lot of these applications that I talked about, they're all sparse in some way or another. This seems to be far more efficient than trying to do remote references.
Okay. How do you handle contention then when two threads try to go to the same memory location?
Oh, that's why we have lots of cores at each memory channel, and they're all multi-threaded. So a lot of threads can land on the same node at the same time, and the fact that we have atomics, very efficient atomics there means when they need to do something where they guarantee that it's just them, there's no race condition there, you just tell it to do it, and it does it. So.
Any additional question? I have one, if you don't mind. So when we do profiling, for example, we improve a part of the code, and then that works well, and something else rises that we didn't expect. So what is the fourth wall that you expect if the current problem?
What's the next wall?
Yeah. If you, assuming that everything will work and the current problem.
That's a good question. Maybe that's where we need to cross over into quantum. That's a good question. I hadn't thought of that. I won't have to worry about that. Hopefully some of you folks will worry about that.
Well, thank you so much.
Okay, good enough.